Welcome to today's paper reading. Today's paper is titled, Latent Diffusion Prior Enhanced Deep Unfolding for Snapshot Spectral Compressive Imaging. This paper was published on AR14 by Zongliang Wu and colleagues from Zhejiang University and Westlake University. The abstract introduces the challenge of reconstructing three-dimensional spatial-spectral images from a single two-dimensional compressed measurement. Existing methods, primarily based on deep unfolding structures, face significant performance limitations due to the ill-posed nature of heavily degraded measurements and the tendency of regression loss-based models to recover images with limited detail. To address these issues, the authors propose a novel approach that incorporates a generative model, the Latent Diffusion model, LDM, to generate a degradation-free prior. This is enhanced through a two-stage training procedure. Additionally, a Trident transformer, TT, is introduced to extract and integrate correlations among prior knowledge, spatial, and spectral features, guiding the reconstruction process to compensate for high-quality spectral signal details. This is the first time a physics-driven deep unfolding method has been combined with a generative LDM in the context of compressive spectral imaging, CASI, reconstruction. The proposed method demonstrates superior performance in both reconstruction quality and computational efficiency, as evidenced by comparisons with synthetic and real-world datasets. Hyperspectral images, HSIs, differ from normal RGB images by containing multiple spectral bands, providing diverse spectral information that helps in characterizing distinct objects. This spectral information is crucial for high-level image tasks and various applications like medical imaging and remote sensing. However, capturing HSIs presents significant challenges as it requires collecting 3D HSI signals using 2D sensors. Over the years, various methods have been developed to address this, including the use of compressive sensing theory and the creation of coded aperture snapshot spectral imaging, CASI. Reconstructing HSIs from 2D compressive measurements is an ill-posed problem that has been tackled using both traditional model-based methods and learning-based approaches, with the deep unfolding network, Yuan, emerging as a leading method in recent years. Figure 1 presents a comparison of the peak signal-to-noise ratio, PSNR, in decibels, dB, against the number of floating point operations, flops, in gigaflops, G, for various hyperspectral image, HSI, reconstruction methods. This comparison highlights the trade-offs between reconstruction quality and computational efficiency. Additionally, the figure includes an ablation study that examines the impact of using different time steps in the diffusion process. The results demonstrate that our proposed method achieves the desired reconstruction quality using only a very limited number of diffusion steps, indicating high efficiency. Figure 2 presents a comparison of error maps and feature maps between the previous state-of-the-art, SOTA, method and our proposed method. The top row displays the error maps, highlighting the differences in reconstruction accuracy. The bottom row shows the feature maps before and after applying the Latent Diffusion model, LDM, enhancement. The enhanced feature maps exhibit a significant reduction in noise and a clearer delineation of edges, demonstrating the effectiveness of our method in improving the quality of hyperspectral image reconstruction. In the realm of diffusion models, significant advancements have been made in generating high-quality samples through an iterative denoising process. However, this method is computationally inefficient due to the extensive iterations required for inference. Latent diffusion models offer a faster alternative with strong generative capabilities but face issues with fine detail alignment and unwanted artifacts, along with high computational costs. On the other hand, hyperspectral image reconstruction has evolved from traditional model-based methods to deep learning-based approaches, each with its own set of challenges, including the need for interpretability and robustness in deep learning designs. Figure 3 illustrates the components and processes involved in the single disperser CASI imaging system and the deep unfolding network, DUN. Part A shows the CASI imaging process where the HSI data cube is captured by a monochromatic sensor. Part B details the GC gap projection, which is a key component in the DUN. Part C depicts the latent encoder, which compresses the measurement and clean HSIs into a latent space. Part D presents the simplified denoiser, which follows a U-shaped structure. Finally, Part E outlines the end-stage Yuan, where each stage includes a GC gap projection and a denoiser. The denoiser in this network consists of 5 trident transformers, TT, each assisted by prior knowledge CGT generated from the diffusion model. The CASI system efficiently captures 3D spectral signals by initially coding spectral data with different wavelengths in an aperture, and then integrating them into a 2D monochromatic sensor. The mathematical forward process of the single disperser CASI, SD-CASI, involves coding the original HSI data, denoted as X is an element of RW times H times N lambda, by a physical mask M is an element of RW times H. This coding is performed through element-wise multiplication. After light propagation through the disperser, each channel of the coded data is shifted along the H-axis, forming a shifted data cube. X is an element of RW times H times N lambda. The imaging sensor then captures this shifted data into a 2D measurement Y, which can be modeled as Y equals X plus B, where A is the sensing matrix representing the coded aperture. The proposed model introduces an unfolding framework enhanced by latent diffusion prior to solve the optimization problem in EQ. 2. This framework employs the generalized alternating projection, GAP, method, which is particularly suitable for deep unfolding networks, DUN, due to its ability to interrupt and resume optimization. A key innovation is the gradient correction gap, GC gap, which rectifies gradients in limited stages. The latent diffusion prior is introduced in a two-phase manner. In phase 1, prior knowledge is learned from clean hyperspectral images, HSIs, and in phase 2, a latent diffusion model, LDM, generates this prior conditionally on the measurement. The trident transformer is designed to aggregate high-quality, degradation-free prior knowledge, incorporating spatial, cross-spectral, and cross-prior flows to enhance the reconstruction of hyperspectral images. Figure 4 illustrates the trident transformer architecture, which is designed to aggregate high-quality degradation-free prior knowledge for HSI reconstruction. The trident transformer consists of 3 main branches: spatial flow, cross-spectral flow, and cross-prior flow. Each branch processes the input feature UI and the prior feature Z to capture different aspects of spatial and spectral information. The multi-scale prior features Z are generated through downsampling layers, providing representations at 3 different scales. The flow interaction and aggregation mechanism ensures that the information from each branch is effectively fused to compensate for spatial and spectral deficiencies, thereby enhancing the reconstruction of hyperspectral images. The experiments were conducted on 3 key datasets: the CAVE dataset with 32 hyperspectral images of size 512 by 512, the KAIST dataset with 30 hyperspectral images of size 2704 by 3376, and the SD-CASI system dataset capturing real-world scenes of size 660 by 714 by 28. Performance metrics used include PSNR in decibels, SSIM, and the correlation coefficient for wavelength accuracy. Comparisons were made on synthetic data as detailed in Table 1, real data as visualized in Figure 6, and overall performance metrics in Table 2. These comparisons demonstrate the effectiveness of the proposed method against state-of-the-art techniques. Figure 5 presents the visualization results on synthetic data, focusing on 3 out of 28 wavelengths for detailed comparison. The CORR metric, located in the top left curve, represents the correlation coefficient between the method's curve and the ground truth curve of the selected, golden box, region. This figure highlights that our method achieves a higher accuracy with a correlation coefficient of 0.9995, outperforming other methods. Additionally, the zoom section of the figure illustrates that our method provides clearer edges on the hat compared to others. Figure 6 presents visual comparisons of real data reconstructions using various methods. 2 wavelengths out of a total of 28 are selected for detailed analysis. The figure highlights the differences in reconstruction quality, particularly in terms of noise and artifacts, with our method showing less noise and artifacts on the plastic toy surface compared to others. Table 1 presents the performance metrics of peak signal-to-noise ratio, PSNR, in decibels and structural similarity index measure, SSIM, for 10 synthetic spectral scenes. The table compares the results of different algorithms, including Twist, DNU, MST++, Bernat, LRSDN, DUHSD9 STG, DDF+3, PADET5 STG, RDLUF Mix S2-3 STG, Hours 3 STG, Hours 5 STG, PADET12 STG, RDLUF Mix S2-9 STG, Hours 9 STG, and Hours 10 STG. Each cell contains the PSNR value at the top and the SSIM value at the bottom. The average column represents the average performance across all 10 scenes, with the best results highlighted in bold. The table also indicates the number of unfolding stages, -3 STG, for some networks. Table 2 presents a comprehensive comparison of performance and computational efficiency among recent methods. The metrics evaluated include peak signal-to-noise ratio, PSNR, in decibels, the number of parameters, perms, in millions, floating point operations, flops, in billions, inference time in milliseconds, and training time in hours. Key highlights include the PSNR values of 38.89, 39.57, and 40.09 dB for different methods, indicating the quality of the reconstructed images. The parameter counts range from 1.89 to 5.38 million, reflecting the complexity of the models. Flops, which measure computational cost, vary from 88.68 to 231.09 billion, showing the efficiency of each method. Inference and training times are also provided, offering insights into the practicality of deploying these methods in real-world applications. Table 3 presents an ablation study examining the impact of different modules within our three-stage unfolding network. The table includes the peak signal-to-noise ratio, PSNR, averaged over 10 synthetic scenes and the floating point operations, flops, during testing for various configurations. Key points include the PSNR values for different module configurations, the flops, G, for various ablation scenarios, and the impact of removing specific modules on performance. This study helps in understanding the contribution of each module to the overall network performance. In this ablation study, the authors evaluated different variants of their model. They tested models with inaccurate guidance, without prior flow, and without diffusion. The performance metrics included PSNR values, flops, and inference time. Key findings from the study indicate that the latent diffusion model, LDM, prior assistance improves reconstruction results. The Trident transformer design successfully aggregates information and compensates for reconstruction defects. Additionally, the study found that n equals 16 for the Z-scale maintains a balance between performance and efficiency. Table 4 presents a comparison of different Z-scale, n, values, focusing on their impact on performance and efficiency. The study finds that n equals 16 provides a balanced outcome, maintaining high performance while ensuring computational efficiency. Key metrics such as PSNR, peak signal-to-noise ratio, and flops, floating point operations, are used to evaluate the reconstruction quality and computational cost, respectively. This analysis highlights the optimal setting for Z-scale in the context of spectral reconstruction tasks. In this paper, the authors introduce a novel deep unfolding network that utilizes prior knowledge from the latent diffusion model for spectral reconstruction. This approach achieves state-of-the-art performance on both simulated and real data. The research was supported by several funding bodies, including the National Natural Science Foundation of China, the Zhejiang Provincial Outstanding Youth Science Foundation, and the Westlake Institute for Optoelectronics. Thank you for watching.